next speaker is Nitin Rajmohan. He's from Akiana, and he's going to be talking about streamlining high-performance RISC-V IP development with Cadence's verification solution. So just a little bit about Nitin. He is co-founder of Akiana. He focuses on hardware, systems engineering, and IP validation. Most recently, Nitin was the Senior Director of Engineering on the ARM server program at Marvell, where he also led CPU verification, validation, and production qualification on the Thunder X3 program. Prior to Thunder X3, Nitin led CPU pre-silicon, post-silicon validation on the Thunder X2 at Broadcom and later Cavium at Marvell. He's part of the team that successfully delivered Thunder X2 for the Astra supercomputer, the first ARM-based system to feature in the top 500 supercomputers. And his prior roles were at NetLogic and Intel, where he worked on MIPS and x86. With that, I'll hand it over to Nitin.
So thank you, Paul. That was a nice intro there. So good afternoon, everybody. My name is Nitin. And today I'm going to talk about what we do at Akiana and how we did what we did at Akiana using the Cadence verification solution. How about now? Good. So my co-author today for today's presentation is Joe. He's not here. He's in the East Coast. So let me just get right into it. So bit of an intro about Akiana. So Akiana is a RISC-V IP solution company. It's a Bay Area-based startup. We've been around for around 4 years now. So what we provide, our product is all configurable IP solutions. We provide RISC-V IP cores, cache controllers, coherent, non-coherent interconnects, AXE compatible, then whole range of system IPs for the RISC-V space. We also have AI IPs, gem engines, and different FP informats. Target applications include high performance. I mean, the IPs we provide can service all the way from microcontroller all the way up to data center, handheld, mobile, client, wearables, automotive. So we have IPs that service the whole range of spectrum. We also have wide vector AI cores in order and out of order, which can integrate with Akiana or customer gem engines. Okay. So what we provide, I mean, the past around 4 years or so, we started from nothing to providing fully configurable IP solution that is fully verified. So we have, whatever that can go into a CPU subsystem, we have all the IPs there. And obviously the challenge is to get from nothing to get to a high performance IP solution that's fully verified and ready for customer use. That's obviously one of the biggest challenges we had. The way our IP works, it's all from a single design database that's configured, and based on the configuration, we can spit out so many different processor configurations. I mean, it's like designing multiple processor or CPUs, all from a single IP source. I mean, based on my past experience, this is like running multiple projects in parallel. We could technically do like hundreds of CPUs out of this single IP. And to add to it, we have interconnect IPs and cache controllers and system IPs. So it does provide quite a bit of challenge. We have built test suites over many years. IPs, today it's running in simulation and emulation constantly, 24/7 full test suites. And we've been doing this for the past, I mean, we have had the IPs ready 2 years back, and it's been getting mature over the past year or two. And we use the Cadence solution. We use the Cadence simulation solution, and also the Cadence emulation cloud for all our verification needs. So challenges. Now, as a startup, so I've been in big companies. In big companies, you have base material collateral to work off. As a startup, we have nothing. We start from zero, which means that we have to do a ground-up development of our IP, VIP, our whole simulation flow methodology has to be developed. And you can't, I mean, the product that we are targeting is cutting edge, high-end CPUs. So you got to have your IP meet those performance goals. Full feature compliance, we are part of the RISC-V. I mean, our RISC-V IP, and we have a RVA23 profile. I mean, if you're familiar with it, it's one of the latest profiles that have come out of RISC-V. And we are fully compatible to it, which means that we have to implement all the latest and greatest features. Add to it, we are a configurable IP solution company, which means the coverage space is just huge. Now, it's one thing to verify one CPU. Imagine having to verify tens of CPU configurations, or maybe even hundreds. So that's a huge space by itself. And the other aspect is, as we can do different IP configurations, we have the ability to do heterogeneous IPs, which means that you can have like 3, 4, 5 different types of CPUs all in a single system. And sometimes it's interesting, for some of our customers to have maybe not 4 or 5, but at least a couple of different CPUs, different classes of CPUs in the same system. So that's another level of challenge. And obviously, though we are IP provider, we still have to make sure, because these are all different pieces that go into a full CPU subsystem. So we need to put it together at a subsystem or system level and make sure that they all work well. They integrate and work well and are well tested. It's a pretty broad IP portfolio that we have. And time to market. We have to do all this in like 2-3 years that we have so that we can get into market and provide these solutions to our customers. So, and when we get to it, it has to be mature. Now, nobody wants to deal with an IP that's not mature. Now, we go and talk to them, say, hey, IP, we are working on it. They say, okay, you come back, talk to us when it's mature. And it has to be ready to integrate into whatever systems that they might have. And all this, being a startup, resources are constrained. We don't have big budgets. Cash is king in a startup, so we got to conserve cash. We got to do all that. So execution efficiency has to be very high. So let's see how we went about doing that. So one of the strategies we took was a modular design. The idea is that whatever we build as IP should scale all the way to different subsystem and system. This helped us to be able to get to the system very fast. I'll show you what that means. Because when we go to customers, they ask for IP, but a lot of the customers want actual subsystems. So we have to be able to put together IP subsystems and give them something. And we have to do it in a very short time. And sometimes it has to be customized. So that adds a challenge, which means that we have to be ready by design to be able to put together these things. So that is one of the strategies. And obviously, iteration. So when we are doing ground-up development, we don't have a baseline. I mean, we know what our target is, but we don't have baseline to work off, which means that we need to be able to iterate very fast. The way we do development is that as we develop, we get into the system level, and we start doing emulation and system level testing, all in parallel, nearly parallel. So because this iteration is critical to be able to push performance. Again, you can design something at a certain level, and then when you want to get into a very high level of performance, it requires quite a bit of iteration, and we have to do it fast. The other aspect is always on subsystem, which means that as we are developing IP, we take it into subsystem, which means that subsystem and system has to be alive constantly, which means that we have to be constantly be able to pull it and constantly be testing it, take in incremental features, any updates, and be able to bring it up very fast. And I talked about the heterogeneous IP, to be able to mix and match different IP configurations into a single system. That way, we get to test our own IPs across different systems. And one of the things about this is, the advantage of doing this heterogeneous is that we can swap out cores. So if you have a specific core configuration that is not working, we can immediately swap out a different configuration that we know works. And we can still keep moving without having to affect execution. So the strategy we laid out, what are our needs? Ease of build and bring up, right? So the tools that we use is very critical to be able to move fast and still attain the high quality that we need. So it should be very easy to build, easy to bring up. Scalable and easy maintenance of different IPs at different levels. Heterogeneous IP support, I talked about it. So the tools need to be able to support it. And it should be very easy, easy to use. Coverage-based validation. Again, there has to be a strong coverage-based validation support because we rely on coverage to make sure that our IPs are of high quality. Debug has to be fast, efficient. We need to be able to turn around debug fast. Though we are building CPU subsystem IPs, we need to be able to put together a system, which means that we need to have access to stable VIPs when we are adding interface IPs. So that is critical, access to range of stable VIPs. Then the other thing we do is we have to have both simulation and emulation because we are building the CPU subsystem. We need to be able to run actual software. So we test our IPs with actual real-world software quite a bit. So that porting and maintenance between simulation and emulation has to be very easy, a minimal overhead. And obviously we provide these IPs to back-end emulation, so there should be rigorous static checking of the code. And on the right side, you can see the Cadence solution that we use. We use the Cadence Xcelium for the front-end simulator, Cadence Verisium for the front-end debugger, Cadence VIPs, and the Cadence Palladium Cloud for our emulation platform, and Cadence Jasper for the LINT CDC. That satisfies all our needs that we are listed. So I mentioned a lot of challenges, as a startup. So in this talk, I'll talk about a couple of them and how we solve them. So one of the things is that configurable IP, right? So what that means is that the way our IP is designed, we have a single system Verilog code base, single database. And all IP variations come out of the single design database, which means that if you want an in-order CPU, if you want an out-of-order CPU, if you want CPUs with certain features, that can go into in-order or out-of-order. It doesn't matter. They all come from a single database. Which means if you're putting together a system, you need to be able to take these configurable IPs and build them in to build different variations of it. And the way we did it, the way our configurations, it's all parameter and define spaced. So we have based on an input configuration. Now let's say it's an YAML input. And it takes an YAML input, and it should be able to spit out an actual, I would say, hardened IP, not a back-end hardened, but a front-end hardened IP. That is like a single CPU configuration that has a specific set of features, which is what we would have to provide to customer. So the way the configuration works, the configuration is one of the inputs into the database that we have. And that's fed into our compile scripts and lab scripts, and that provides the actual compiled model, simulation model that we have. Because we are using the same database, we need to compile each of these IP variations separately and then put them together. So the way we do it, we build them as libraries, and we'll talk a bit about that there. But each of these IP variations or configurations is compiled separately as libraries. And that's the IP aspect of it. But then we have the VIP aspect of it that needs to go with it. And we cannot use the same. We can use portion of how we do the IP as libraries, but VIP, there's more software aspect to it. So we need to be able to build packages out of it. So that requires some additional handling, special handling, to be able to have VIPs that are specific for each IP as a package and still work together in a single system. So the way we did the test bench aspect of it, right? So the IPs were built as separate libraries. the test benches, we had another level of redirection. We used to define for the IP name itself. And then when we hooked up the interface and compiled, and we compiled it as packages. When we did the packages and hooked up the interface, we basically specified the name at the time of build. So the hardening happened at that time when the IP got compiled. And along with that, we specified the name directly into the compile script also in Xrun. So with this two level of, or maybe 2 or 3 levels of redirection, we were able to get these VIPs built with the IPs, different variations of it in a single shot, to put together a more complete system. One of the challenges we had was that, and the reason we had to do that was because Verilog 2001 standard doesn't provide a way to do it in a very seamless way. I mean, they do it for the IP, the hardware, the RTL side of it, but not for the UVM packages side of it. And so we had to go down this path. I mean, it's something we had to do this discovery because it was not something obvious. So we had to try a few things before it actually worked for us. And one of the things about that was that from a tool standpoint, Xcelium was we didn't run into any tool issues with that, the way we did it. And it's very scalable. The whole methodology we built, we could today build any number of configurations we want and put together in a single system, no issues. And the nice thing about this is that because emulation uses the same front end as Xcelium, it is scalable into the emulation platform also. So we can seamlessly, I mean, if it compiles, there's a high guarantee that it'll work in emulation also. So it gives us a very seamless flow to move from simulation to emulation. It's a bit more about the compile itself. And then once we have this piece, right, now we have the ability to compile each variation or each configuration IP in different, in a single compile or in a single build. We can do the mix and match. So again, I mentioned the reason we do this heterogeneous IP is that we can put together this and verify different variation of the same IP in a single system and see how it works. And we actually get actual system level feedback. We get performance feedback. We take the same database into both simulation and emulation. So especially when we are pushing performance features across different configurations, it is critical we get that emulation feedback. And this is very critical to it. This helps us get that in a very fast. So give you guys some idea about how much this whole process takes. Let's say we're adding a feature. Or let's say it's a feature, we are making enhancement to a feature, right? We make a RTL change. We compile it in simulation. We know it compiles. By the end of the day, it has gone through reasonable regression. And we know it's reasonably stable or reasonably healthy. The same day, by the end of the day, we can take it into emulation. By next day, we have an emulation platform that is booting Linux, and we can start running our software on it and get performance feedback. So within a span of 1 to 2 days, we have actual performance feedback from system software that we can take it into our IP and spin it around. And we can do this. I mean, if we can iterate through this, we can do this like 20, 30 times in a month. Suddenly, the development speed increases quite a bit. Obviously, we would hit hiccups. Sometimes we add a feature, it doesn't work. It doesn't work on a specific configuration. And this is where the heterogeneous, the configurable IP comes in the picture. We swap out immediately. Okay, we know this, we add this feature. This feature is applicable to multiple different variations of this IP. So can we swap it out? So we go and swap it out and put it in a different configuration and then try it out and see if that works while we are trying to fix bugs with this other configuration. So again, we are constantly moving. We are not stalled. And the methodology basically enables that. So closing words, I mean, what I talked about was 2 of the specific challenges. But I mean, as a small company and the scope of what we are doing, there are a lot of other challenges we have to deal with. And the tools that we used were critical to help get to where we started to where we are today to be able to deliver mature solutions to our customers. So the Cadence verification solution was critical for us to get to product readiness in a very short time. It enabled very fast development, quick debug turnaround, and constantly be able to move fast. And at the same time, not compromising quality. I mean, when we give products to customers, they want the highest quality possible. They don't care who's giving it. They want the same quality as any other big companies give it. And you cannot compromise on that. So we're able to provide that high quality, cutting edge technology in a very efficient manner. And that is it from my side.